Hello, this is Nefi Varela, and this is my third video for this fourth unit. And in this video, I'm going to talk about the lungs. And I'm going to start talking about pressure and membranes. There are going to be three main pressures that are going to play an important role: an inspiration and an expiration. Okay, so an inflating our lungs. The first one is going to be atmospheric pressure. At sea level, atmospheric pressure is going to be 760 millimeters of mercury. But in this case, we're going to consider it zero for this scenario. We're going to have also alveolar pressure. The alveoli are going to be some like microstructures found in our lungs that are going to help us in the process of gas exchange, oxygen and carbon dioxide, and carbon dioxide exchange. And this one is going to be -1 during inhalation, and during exhalation is going to become more positive. So in this case, can reach even to 1 millimeter of mercury. Okay. Now we have pleural pressure. And now is where membranes start playing a role. Surrounding the lungs, covering the lungs, we're going to have a membrane called the visceral pleura. As the name implies, it's covering the lungs. In the costal, close to the ribs, in the costal side, we are going to have this called parietal pleura. And between them, we will have this called the pleural space. The pleural space is going to be full with liquid. This liquid is going to be facilitated by the lymphatic vessels. Those are going to dump liquid in this cavity, make it creating a negative pressure in that space. That space also can become more negative during inspiration. How that's going to happen? Our lungs are like a rubber band. I don't know if you can see here my screen. They have the tendency to collapse because they have elastance. This is elasticity. So if we stretch them, they'll want to return to their original space. So this is a lung shape. So this is going to be like a vacuum that is going to pull the lungs in this shape, avoiding them to collapse. So imagine this finger in the pleural space is going to create some pressure, maintaining the lungs in this shape. As we inhale, we will want to increase the size of the thoracic cavity. We're going to use muscles as the diaphragm that is going to contract and and adopt like a curved shape, making more space, creating more space in this in this cavity, in the thoracic cavity, and being able to create more pressure. So that's gonna pull the lungs somehow. Okay. We have also accessory muscles are the internal intercostals, external intercostals, even the pectoralis minor can play a role, the sternocleidomastoid. But now let's just focus in the diagram that is going to go down during inspiration, making some space for our lungs to increase volume. So that's pretty much it with pressure. Something else to mention, the difference between alveolar pressure and pleural pressure is going to be transpulmonary pressure. And this one is going to become more negative, sorry, as I described previously, as the alveoli and the lungs are inflated. Okay, now the alveoli. I've been talking about the alveoli, but what's the alveoli? So those are going to be like small branches in our lungs. So we have the bronchi and the bronchioles. And now then we're going to have these like really tiny structures named the alveoli. And to illustrate that, I have here something that is going to help us to visualize it. I have some flowers. So imagine these are our lungs. In our lungs, we're going to have the bronchioles and then the bronchioles. And here, imagine these small, tiny flowers are going to be the alveoli. And in the alveoli is where gas exchange is going to happen. I'm going to describe something named the law of Laplace. I think that's how you pronounce it. That is going to play an important role in this gas exchange, in this filling with air in the alveoli. Okay, this law means that pressure is equal to 2 surface tension over radius. Surface tension is the strong attraction of water molecules on the outer space to bind to each other. So, in other words, it's like the affinity, the attraction of water molecules to be together. Imagine we have like a tank of oxygen, right? And then I'm gonna draw some particles. Those are gonna represent oxygen. As we decrease our volume here, those particles are gonna be more tight together, right? So they're gonna start like pushing to each other, and we are going to create more pressure. So as we decrease volume size, we are going to increase pressure. So I want to translate the words to more mortal words. As we decrease radius, we are going to have an effect in surface tension. And that's why this law is describing. At a small radius, we're going to have high pressure and also high risk of collapse. Okay, a large pressure, we're gonna have a large radius, sorry, we're gonna have low pressure, and air is gonna rush from the high to low pressure. So this is what is going to happen. We have this bronchi that is big and this one that is small. This one is gonna push the air out of it that is gonna be taken by this one because of its radius. Air will want to go to this one, and also all the air coming from the exterior, it's gonna go to that alveolus with a large radius. That is not good. Okay, we don't want that. So our bodies create something called surfactants. Surfactants are gonna be amphipathic molecules. That means that they have a hydro philic exterior and hydrophobic inside. And these are gonna reduce surface tension and are gonna help us to equalize pressure. So with surfactant, with this liquid in here in the alveoli, we're going to reduce surface tension and we're gonna equalize pressure, okay? So now there is no risk of collapsing for this bronchi with small bronchi, no, alveoli with small pressure. And in the large one, also, we're gonna have the same effect. We're gonna reduce surface tension, equalize pressure, and now, because the pressure and tension in both of them are gonna be the same, air is gonna equally fill large and small alveoli. There are some pathologies that can um, affect this. For example, for premature babies, when they born a couple weeks earlier, they don't develop this surfactant because, of course, babies don't breathe the same way as we do. So that makes harder, more difficult oxygenation and ventilation. Okay, so we will be leaning more towards this situation, and it's not good. Usually babies are put in a high concentration of like incubators with oxygen in high concentration to help them. I've been talking about two things, elastance and compliance. Elastance is like this rubber band, like this tension that is created by an object that it facilitates to return to its original state when it's stretched. I'll describe it like that. Compliance is something more related with volume. Here we have a graph that is the relationship between volume and pressure, being pressure in the x-axis and volume in the y-axis. So in a healthy, normal person, during inspiration, we're gonna have this isovolumic period where we need to increase pressure to start inspiration, to start that filling with air, to start that increasing of volume. I don't have a balloon with me, but I'll say that lungs and balloons work pretty similar, right? Maybe because even they have the same shape, but I have here a Ziploc bag, okay? So I'm gonna describe it like this. Imagine that we need to increase pressure. So I'm gonna increase pressure, but I'm not gonna start to filling it with air. So it's gonna happen something like this. And eventually, when I reach this like threshold, our lungs are gonna fill. Now, to decrease it, we need to also apply some pressure to decrease volume. So that's gonna happen during expiration. But when we increase elastance, imagine that, for example, this bag had thicker plastic, right? Filling it with air will be something harder to do because it's harder to pull this bag apart, like to fill it with air. That's what I'm trying to say. So during elastance, with higher elastance, we need a really big pressure to increase volume. And of course, because we have that higher elastance, we're not going to increase the same level of volume. Okay, so that's what is this graph representing. We need a lot of pressure, and we are not going to fill it with a lot of volume and return to its original state. We need to have a lot of decrease of pressure to decrease volume. Okay, so that's pretty much it. Compliance. Again, compliance is almost equal to volume. Compliance, in this case, we don't need a lot of pressure, but fast is gonna be filled with volume. That's like a balloon with really thick plastic, right? We don't need a lot of elastance, and then we're gonna increase easily this volume. And also, we don't need to decrease this pressure way too much to decrease volume. So elastance is gonna be equal the change of pressure over volume, and compliance is gonna be the change of volume over pressure. There are some abnormalities that are gonna, for example, increase compliance. That's a case of smokers or people with pneumonia. They're not gonna have a hard time having inspiration. They can do it pretty easily, but expiration is going to be something difficult. Um, Talking about pressures and problems, pathologies, pneumothorax. Pneumothorax happens when we have a puncture in our lungs, and that puncture is gonna let some air to escape from the lung to the pleural space. As I said previously, that pleural space is like a vacuum that is gonna avoid our lungs to collapse. So if we increase pressure there, the pleural space is going to become more positive. And as it becomes more positive, that vacuum stops working. And eventually, the lungs are going to collapse. So for this first question, for this third question, I'm going to stop here. And in the next video, I'm going to describe gas exchange. So I hope you liked it. And that's it. Wait for the second part.